Hello, I'm going to present the EMS3. It's an improved algorithm for finding edit distance-based motifs. This is the final project for the computational biology course of the Institute of Computing in the Universidad Estatal de Campinas. So let's start. What is a motif? A motif is a pattern that occurs in all the elements of a set of biological sequences. The formal way of viewing it is given a set S of n strings with the same length n over the alphabet sigma. A string S is a motif if and only if S is a substring of every string of this set S. Now, motif search is a problem that requires to find all the motifs from a set of sequences. It has some variations. In this case, we have the planted motif search, which is a variation in which all the strings M of length L are considered a motif if each of the strings in the set has at least one substring with a Hamming distance of at most d with respect to M. In addition, we have our variation, which is the EMS, the distance-based motif search, which also allows insertions and deletions. So while the PMS uses Hamming distance, the EMS uses edit distance. Finally, we have the quorum edit distance-based motif search, the QEMS, which allows quorum support. In this case, we're going to have an extra parameter q, so that each motif must occur in at least q times n of the sequences. Notice that n is exactly the same of the size of S. Now, two algorithms were proposed before this algorithm EMS3, which are the EMS1 that uses the neighborhood trees. However, it uses a lot of memory and also generates many duplicate candidates. It was proposed in 2012. For the EMS2, which was proposed in 2015, it kind of fixes some of the cons of EMS1 in this case by adding wildcard characters on the D neighborhood trees, which allows a more compact representation, and defining 9 rules to avoid candidate duplicates. It also has a parallel version that was implemented on the same paper. Now, it's important to use and define parameters. We are going to have a parameter L and a parameter D. In this case, L is the size of the string that is going to be a motif, and remember that D is going to be the maximum edit distance between this motif and the substring in the biological sequence. So choosing D to be small or big actually influences on the number of spurious motifs. If we define D to be very large, it's going to be more likely to have a lot of spurious motifs in that way. And if we define D to be very small, we're not going to have a correct answer, maybe, or we're going to have two low motifs, right? Now that an instance is challenging if L is the largest integer such that the expected spurious motifs is close to and greater than 1. This means that if we find a candidate set, then the size of this candidate set is going to be very close to it's going to be expectedly very close to the actual answer. Now we must define a D friendhood and a D neighborhood, which is related with the EMS 1 and 2 algorithms. This is going to be based on the parameter L of the problem, and it's going to take an input string U, which is going to be an Elmer. Now, a D friendhood is a set of Elmers which have an edit distance exactly of D from the input string. A neighborhood is just very similar. It only means that it's going to take every element that doesn't exceed D on the edit distance. It's easy to see that the D neighborhood is a superset of the D friendhood. Now we're going to use two approaches, which are the pattern-driven approach that generates all the possible patterns given the length and given the alphabet, verifies each pattern in the sequences, and it doesn't actually work well with the EMS because at the distance is time consuming, so generating all of them and testing all of them is going to be too slow. And we have the sample driven approach, which uses the binding sites and sequences to generate candidates for each string in S. So it's going to just generate substrings of each string in S, and in the end they are going to be intersected in some way with the final candidate set. So our algorithm is going to use both of them. Now there's this technique that is called projection, that it actually reduces the size of the input in a way that we don't lose correctness and we are always able to return to our original state. In this case, input size is always desirable to reduce it because most of our EMS solvers actually depend on the size of the set S and also on the size of the alphabet. So if we are able to reduce the size of the set S or reduce the size of the alphabet, then we are kind of good in improvement. We have this random sampling technique that we can just take some number of sequences that is smaller than the original one, and we want to compute their motifs. In this case, we can consider this as a projection method, since each motif should appear in every string of the original set. Then it in particular must appear in all those randomly chosen sequences. Our final idea is going to be to project the sequences and reducing the alphabet size. Now the algorithm consists of 5 steps. First one is dividing, that is taking the random sequences. We're going to denote I1 the sequences that were chosen and I2 the other ones. We have the compression part that reduces the alphabet size, projecting sigma to sigma prime. It's pretty similar than the random sampling, but in this case is for the alphabet, and this is going to be only applied to I2. And then we have the step 3, which applies the EMS solver to both I1 and I2, and we're going to denote their output as C1 and C2 respectively. The fourth step is going to be merge, that filters all the elements in C1 such that their compressed string appears in C2. And in the end, we're going to verify all the candidates and compare them with the strings in I2. And we are going to have two algorithms for this. The first one is just a brute force over the elements and using dynamic programming. The second one is a DFS on the D neighborhood and hash table, just to check if they exist or not. So these 5 steps are going to solve this problem correctly and hopefully efficiently. Regarding the correctness, we must see that the compression of the alphabet doesn't really increase the distance between the strings, because some characters that originally will be different may be projected to the same one, so some mutations of the edit distance might be deleted in this case because they are just going to be the same character. So it's valid to compress the alphabet this way. And in addition, for I1, every motif must be included in C1, since they at least must appear in every string of I1. If they do not appear on every string of I1, then they couldn't be a motif at all. And for I2, Since the compression doesn't really increase the distance, any compressed motif must appear in every string of I2 as well. So what is our conclusion? That every motif is included in our output. Notice that this output is from the step 4. That is before verifying. After verifying, we're going to see that since every motif is included in our output, then our output is going to be a correct answer. It's going to be exact, the answer. Now, projecting the alphabet is important, as I said before, because our EMS solvers rely their performance on the alphabet size. However, despite this reduction improves performance, the number of spurious motifs increases. And we are going to have that the candidate expansion becomes hard and time consuming. Because since we're projecting many characters to the same one, when we would like to return to the original state, we are just going to have to try every single possible character that was projected into that character to check if the original string or data actually is it actually is the same as the one that we are requiring. So reducing the alphabet is good, and it might be a little bad in this case. So we must balance it. For the part of balancing, we're going to base on the expected number of candidate motifs. Notice that our goal will be that the expected number of candidate motifs is exactly the same as the exact number of motifs, or at least the expected number of motifs in this case. But we're going to have these formulas. They were developed on the EMS2 paper. We're not going to go too deep into them. Just notice that the last formula, the number 4 one, has all the parameters that we already have, and it represents the number of candidate motifs given those parameters. Now the expected sizes of C1 and C2, they are obviously replacing our parameters into the formulas. There's no magic in that. And the expected number of Elmers in C, which is going to be our final candidate set. Notice that C1 and C2 are like the candidate sets before merging, and C is the result out of after merging. We require an Elmer to be in C1 and that its compressed version in C2. So we must compute or must analyze the probability of an Elmer to be in C1, which is P1, and being in C2, which is P2. However, we have that many Elmers are going to be projected to the same one in sigma prime, which is the one that is, which is the main is I2 and C2. We're going to have that the expected number of Elmers is going to be sigma to the power of L, which is the total number, multiplied by the probability of being C1, multiplied by the probability of being C2, compressed over epsilon 2 to the power of L, since they are going to be projected to the same Elmer. In addition, we have that the time complexity of EMS2 is this formula. This expression actually gives us some ideas regarding the NP-hard, the non-polynomial class of this algorithm. Then the time complexity for verifying motifs depends on the size of the candidate set, also on the other parameters. Notice that the first one has some L squared, which is roughly about the dynamic programming part, and the algorithm 2 doesn't have it because it uses hashing and hash tables to compare to check existence of some of these strings. So, the expected time complexity of the EMS3, we are going to see step by step. The first step and the step 2 are negligible because they are almost linear. The step 3 is this one because we're going to just replace this formula of the EMS2 in the sets of I2 and I1. We have this merge part that we can actually compute C2 sorted, so we can use binary search to search for the for checking existence of the compressed version of each string of C1. And the last but not least is the verification algorithm that is going to be assumed to use the algorithm 1. So the total expected complexity is this monster. Notice that n prime is actually epsilon 1 times n, and sigma prime size is going to be epsilon 2 sigma size. Now, we might be interested in balancing those complexities on I1 and I2. So we are going to set some guidelines to choose the parameters. The first guideline is that if we want to reduce the number of expected motifs, we require that P2 over epsilon 2 to the power of L is less than 1, just as the expression that we seen before of the expected number of motifs in C is equal to the number of Elmers, which was the size of sigma to the power of L times P1 times P2 over epsilon 2 to the power of L. We are going to take that, and if we reduce it the most, then we are kind of improving our expected complexity on the number of motifs. The second guideline is based on balancing the third step, as I said, and we can analyze the time complexity of the EMS2 on the both sides on I1 and I2, and we're going to deduce that epsilon 1 should be theta of 1 minus epsilon 1 times epsilon 2 to the power of d. And the third guideline is going to be using any analytical or numerical method to minimize the time complexity, according to epsilon 1 and epsilon 2. The three guidelines are valid and would be interesting to play with, but in the paper of the EMS3 they don't actually play that much. An extension to QEMS, the QEMS problem can be solved with EMS3, but we must add an extra parameter epsilon 3 to solve it, because since we are reducing the number of sequences for I1 and I2, then we must consider that for I1 the value of Q must be reduced. In the case of C2, it doesn't really matter so far because it is compressed. It isn't in a compressed way, so we cannot guarantee some things on that. We're just going to use the candidates on the original queue, but in the left side, which is the I1, we're going to use something different. Obviously, some conditions must be held on epsilon 3 for correctness, and all the algorithm remains the same. Just change the EMS solver for a QEMS solver and the parameters. Then we have the approximate EMS3. We can just make it an approximation algorithm if we remove the last step, because it filters the true motifs. If we don't filter, we have a superset. So we're going to have an approximation factor of an expected approximation factor of the expected number of candidate motifs over the expected number of motifs on the set of strings. Now for the experimental results, we're going to, it was the test generation was with 20 sequences with length 600, which is the standard setup for DNA. In this case, obviously, the alphabet is going to be A, C, G, T. And a random string M of length L was generated, which is going to be our motif. In each sequence, a random D neighbor of M was inserted. Test results: 1,000 true motifs and 1,000 false motifs were generated as candidates for testing. When D is small, it was seen that algorithm 2 outperforms algorithm 1 in terms of time. In terms of space, it's almost the same. When D increases, algorithm 1 outperforms algorithm 2 in both time and memory. Algorithm 2 consumes too much memory. Too much memory is it's too much. So we can just try to deduce which one to use according to the value of D. Now the performance comparison using the first algorithm for motif verification sets some speedups that are greater than 1. We have that EMS3 outperforms EMS2 on synthetic real data sets. We've seen that EMS3 actually works more efficiently with bigger instances and also works efficiently with challenging instances. So it's pretty interesting that way. Some interesting parts are that even in the original EMS2 sequences that were kind of tested a lot to have a very good performance, even in those, the EMS3 actually has an speed up of at least 1.3, an approximation. Finally, further research includes improving the EMS solvers to reduce memory consumption. We have seen that if we reduce memory consumption, then we might as well be able to solve bigger instances. Adding quantum support for existing EMS solvers, obviously to solve the QEMS problem. Also analyze different projection methods for the other parameters. We have seen projection method for N and for sigma. In this case, we might as well want to have some projection method for L, D, or M. And finally, designing approximation and randomized algorithm for the EMS, which is have been being developed from 1,192. I think that's all. I hope you have enjoyed this presentation, and thank you all.